Okay, the way we're going to go about this bootcamp is there is a very small, tiny little update to the starter notebook. We'll go over that real quick and maybe tell you some nuances about the blank token, the padding, and some things you need to keep in mind as you go through homework 3, part 2. We will then go over part 1 in detail and then come back to part 2 in detail. Um, Right. So to start off with the update, one, the Piazza post is up. So keep an eye out for that. Um, Otherwise, this is what the update looks like. The mapping dictionary from CMUDIC to Alphabet now no longer has the pad token explicitly. It only has the blank token here, which we expect you to use for both as, of course, the blank token, as well as its index for padding. And something you need to keep in mind is when you're padding your X's, your features, or your MFCCs, the whole idea is that the padding should contribute zero information to your computation, which is why a floating point value of 0.0 tends to work the best. 1 second, I will wait for it. Right, sorry about that. So ideally, it's supposed to not contribute any information, which is why 0.0 tends to work really well. And it's also the default for most padding functions in PyTorch. However, when you're padding your labels or your transcripts or your Ys, you need to be careful about what you're padding it with. It should ideally be an integer value corresponding to whatever points to your padding token. And here the integer value 0 works because we'll be reusing this token for both purposes. Yeah, that's it. And you should also probably take a look at this post here and the very low cutoff logs, which will tell you how the training should go in the first 10 epochs for the very low cutoff model. If there are any questions, please feel free to post them on this post or on the post about the starter notebook update. Either works. All right, I think with this, we can switch over to Appa and he'll go over part 1.
Yeah, sure. Let me share my screen. Wait just a minute. I think I'm sharing a different screen. Yeah, can you see the screen? Is it the PPT? Is it the PPT screen or the other screen?
PPT.
Yeah, cool. Yeah. So hey guys, welcome to the bootcamp. So I'll be going over the first part of homework 3, and from the experience of a lot of people who took this course last semester and the previous semesters, this part 1 might be the hardest part 1 among all the homeworks, but don't worry. If you go the write-up and a couple of tips in this bootcamp properly, you'll be able to complete part 1 pretty easily. So moving on to analysis by of every question. The first question is Rn and cell forward and backward. It is a very simple and straightforward question. You just have to like code this equation in forward and take the derivative of this equation in backward. This is very similar to how you did linear, how you computed the linear weights, linear.py in homework 1. So you can just follow that same pattern in this question for Rn and cell forward and backward. And the next question is Rn and phoneme classifier. So this might be a conceptually difficult question to understand, especially the backward. Forward is pretty straightforward, so you don't have to worry anything about it. You just need 2 for loops to traverse through the time steps and the layers. If you can actually figure out a way without 2 for loops, just let us know. We are also looking for any other good implementation. We are open for it. So backward is kind of tricky. So tips to maneuver this backward and Rn and phoneme classifier is you just have to like understand how the gradients are flowing in the backward diagram. So we have given 2 diagrams in the write-up. One is this, and the other one is just for one time step in the backward. just go over the diagram first, try to understand how the gradients flow in the backward direction, and then just follow the pseudocode which we have provided. So if you just do those two steps for backward, you'll be able to complete it pretty easily. So the next question, the next question is GRU cell, and GRU cell might be one of the longest question in this homework. So forward is pretty okay. You just have to follow these equations which you might have seen in class. So the R, Z, N, H, all the equations. So it's pretty easy to code these equations in the forward. But if you can actually code your forward in a specific way, it'll actually be helpful for you to code the backward also properly. So I'll be going over that first. So forward, you can actually complete it pretty easily. For testing the backward, the first thing I would suggest you to do is that you have to try to modify test group in the autograder files, because to make sure that your final output dx and dh match, you need all the dws and dbs to match properly. So you have to take care of it. So modify the local autograder accordingly. So you have to do that. And I would actually want to share how I did grew cell forward and backward, which helped me to complete this question in like 2 or 3 hours actually. So you don't have to spend a lot of days for it, which people actually do. So the easiest way to do, but it's not the shortest way to do. It's actually to decompose every equation to its most smallest form. So if you can consider the first equation which I've given here, A is equal to tan h plus tan h of an affine function over here. So you can decompose this big equation as small equations as so z1, z2, z is equal to z plus 1, a is equal to tan h. So the forward for this A equation is basically all these 4 equations. Yeah, these actually have 4 lines of code, but backward is now pretty easy to understand if you can see. So if you want to take the get the backward of the initial inputs like x and h, what you need to do is you basically need to go backward from in the opposite direction. So given dA, or the derivative of loss with respect to A, that's usually the input for any backward function you might have already known until now. So given that, you can, from the last equation, you can compute the derivative of loss with respect to z. And with the derivative of loss with respect to z, you can compute the derivative of loss with respect to z1, z2, which is basically backward in this equation. Then after that, you can compute the derivative of loss with respect to w, h, the previous equation. So I hope you all are actually able to get a pattern. You do forward in this direction, and you just do backward in the opposite direction. This is a pretty long but very easy way to actually complete groove cell backward and forward and backward. You can also implement it on your own, but this seems to be a little bit easier for debugging and everything also. So this is something which I wanted to share about groove backward. And the next one is groove inference. Groove inference is basically a groove cell, and for prediction, you just use a linear projection layer. And people usually don't face a lot of issues with it. Issues are usually caused in groove backward. So this should be fine. You'll be able to implement it pretty easily. And yeah, moving on to the next part of homework 3 part 1, which is CDC based questions. So one thing which I would suggest is you can actually follow the pseudo codes which are given in the slides. So those are lecture slides. Those are actually enough for you to complete all the questions. The only thing which you need to do is first understand all the forward, backward, every algorithm, and then try to implement it on your own based on the slides. So that's something which you need to do. And we have given a couple of examples in the write-up for you to understand the math behind it. So you are free to go over these diagrams, write the math on your own, and understand the concepts. So just a minute. Yeah, we have also given examples for forward, backward, and the posterior probabilities. So you just have to go over the math try to understand the concept, and it's easy to just follow the pseudocodes given in the slides. That's more than enough for you to actually complete this question. And yeah, moving on to the last part of homework 3P1 is just a search. The decoding part, whether it's greedy search or beam search. Greedy search is basically like taking the most probable output at each time step. So outputting a probability distribution, you just take the most probable output every time. And after that, you just need to compress the blank spaces. Yeah, this you should have actually seen it in the lectures. And that's it for beam search. Sorry, greedy search. And yeah, a few tips to do this is this: you can actually write your own compress function separately, and you can actually complete this question without a for loop. So there are ways to complete without a for loop with just 4 lines of code, but it is not necessary that you have to do it in that way. If you even if you use a for loop, you won't get a timeout error in Autolab, so you can do it however you want. Just putting it out there that you can do it without a for loop. Yeah. Moving on to the last question of homework 3P1. Beam search is one of the hardest question to understand and implement. But following some steps, you will be able to complete it pretty easily, I guess. So the first thing which I would suggest you to go over is that if you don't have a clear understanding of what beam search is, first go over the lecture slides and try to understand what actually beam search does. So that's the first thing which you need to do. And the pseudocode or the code which is given in the lecture slides, that is more than enough. All the functions, the initialize paths, prune, extend with blanks, all the functions are actually enough for you to complete. You can just re-implement that function in your own code, but you just have to be aware that the pseudocode in the slides is actually not in Python. So I'm guessing it's in MATLAB or another similar version of it. So there, the curly braces do not actually define sets as in Python, and the square braces do not define the lists. So you'll have to think about what lists are like based on the implementation of it. Lists have repeating elements, and sets do not have repeating elements in Python. So you'll have to think about for which variable from the pseudocode you can actually use a list and set. So you have to think about that. Then another thing which I wanted to share is people often complete all functions in beam search and try to say that their final path is not actually matching. Please don't do that. That will be very hard for you and us to get it done right, and debugging will be a pain for everyone. So the more efficient way for you to do is complete each and every function separately. So for example, if you're following the pseudocode given in the lecture slides, you will first complete the initialize paths function. So the initialize paths function in the pseudocode here. So after completing this function, just break the flow in the for loop. So break the for. Okay, here you don't actually have a for loop. So just break the flow here and print all the outputs of print the outputs which are returned. New paths with terminal blank. All these 4 outputs. Yeah, all these 4 outputs. These should actually match to whatever we have given in the green box over here. So the green boxes in the write-up are the outputs of each and every function for just the first test case in the local autograder, and it is just for the first time instant. It is not the final output, it's just a first time step output for the first test case. So after completing one function, print out all the outputs, verify with the green box over here in the write-up. Then after that, complete the next function, verify with this output given here. That is the most time efficient way for you to go over this question, or else you would need to actually spend a lot of time for it. So I would suggest you to go over in this fashion. And apart from that, there is actually nothing that needs to be covered in part 1. So are there any questions regarding part 1? Okay.
No.
Okay, cool. If there aren't any questions, I'll hand over to Abu and Pranav for part 2.
Yeah, thanks,
Thanks,
Apajit.
Apat.
I just want to mention that as I've been putting in the comments, I really cannot recommend two things enough. One, decomposing your equations for GRU. It will make forward and backward so much less daunting than it would be. Second is making a computation graph that will make things instantly clear, and you'll be able to visualize how information is flowing and where it's going. And third is the quiz that relates to beam search is also a very good way to understand how beam search is working, because you'll be able to work through it manually. So those three things should hopefully help you a lot in doing homework 3 part 1. Pranav, take it away.
Okay, thanks, Aparajit. I'll share some slides for homework 3P2. Thanks to Aparajit and Urvil, we got these slides. So yeah, about homework 3P2, this is an automatic speech recognition problem. Professor Bhiksha has already talked about it, what the problem is, why this problem arises, where we have order synchronous data, but we do not have time synchronous data. And so before I dive deeper into how you would want to train your models for this particular homework, some logistics first. Early submission is due on November 7th. I know it's soon. But if you try, you can make it. The Kaggle submission requires a Levenstein distance of less than 30. This would be achievable in less than 10 epochs. And training your models should not take more than an hour. There is also a Canvas
Excuse me,
quiz.
Pranav, the early submission is November 3rd, not 7th.
Oh, I'm sorry.
Yeah, so that's a
Yeah,
typo. So it's not 7th case, it's the 3rd. So
Okay.
it's more sooner than you think.
Yeah, it's much more sooner than you think now. Sorry for that. And but I still feel you can make it if you follow this boot camp thoroughly. We have turned most of the questions into actionable insights, how you can change your notebook and how you can code it out. So there is also a Canvas quiz, which we recommend you to take. It has got some hidden hints on how you should define some of the class objects for your CTC laws and how to decode them as well. The on-time submission is on November 17th. And yes, that's about, I cannot find my cursor. Just a second. Let me get the Zoom thing out. Yeah. Okay, yeah. Training time will not be as high as for homework 2P2. This time the homework is simple, but be sure that you cannot use any attention mechanisms here for this homework, and also focus more on your architecture for this homework. The problem at hand for this particular homework is that we have an input utterance, which is 15 dimensions. So as we have seen in homework 1, we have a 15-dimensional MFCC input frame, which passes through the model, and we want to produce the sequence of phonemes, which in this case, you have an example here. The features are the same as homework 1P2. The labels have changed. We do not have a frame level. We do not have labels on a frame level. But what we have is an order synchronous sequence of labels, but there is no time synchronicity amongst them. So the only way you can use the most probable way you complete this homework is by using CTC loss, and the metric which we use to evaluate your submissions would be Levenstein distance. I hope you all know about Levenstein distance. We have recently shifted from CMU DIC to ARPABETs because they are much more industry standard and are being used in Wave 2, Wave 2. So you can mention about this in your resumes as well if you want. Why is Zoom creating so much of an issue? 1 second. Let me move this down. Yeah. While moving forward, while creating your data loaders, you may see that your recordings are of variable lengths. So a model cannot take input of variable lengths to inside its forward function. You have to pad these variables, you have to pad these input utterances or these MFCC coefficients to be of the same length. And the only way you can do it is by padding and packing. There are some helpful functions by PyTorch, which I will go through when I go through the starter notebook with you all. So you can pass the same input object or the MFCCs for each recording and pass it to a pad packed sequence, which is available in PyTorch, which will just pad everything out for you and return an object which is of some batch size, one time step. So it pads everything to say t equal to 100 and 15 dimensions as in the MFCC coefficient dimension, as mentioned here. Yeah. You do not have to do this for the entire data set. You can do it batch wise. That will also reduce some complexity. And this is a slide just like outlining how packing is done. You have various elements at the first time step. What you do is that you sort them in descending order. Sorting them in descending order will help you then transpose all or pack all of these elements in a concatenate them into a 2D tensor such that you have alternating elements in your 0th index, then for the first index, second index, and as we go forward. This is how a final 2D packed tensor would look like. And these packed tensors are now ingestible by LSTMs and can improve your processing speeds once you batch them into such packed tensors. I will go through the parts of a sequence model here, the embedding layer, the sequence model, and then the classification layer. The embedding layer is basically a convolutional network which you can use to expand upon the number of features that you have. We currently have only 15 features for each MFCC. So you would want to create, you may want to use convolutional neural nets, some CNNs, or either an nn.embedding to find more features for your input. You will then pass this particular input to a sequence model such as LSTM or GRU, which would then go into the final classification layer for you to predict which particular phoneme to pick. The embedding layer is optional but recommended. It is used to increase the dimensionality of the input, as I mentioned. Here is an example. So suppose you have 3 words, deep neural net, and as we know, text can be represented as one-hot encoded vectors. But these one-hot encoded vectors have a lot of information between them. We can see the context ahead, and also from the context behind, we can derive some meaningful information. So what we do is that we move from a one-hot encoded input of words to real valued vectors, which we call text embeddings. These text embeddings can be of various shapes. You can design CNNs as per your liking. You can also get some influence from your previous homework, from homework 2P2, about how did ResNets work, and a connex block. You may simply put in a connex block or a ResNet block to see what happens. There would be a lot of experimentation here with the embeddings and also with the sequence model that you have. So please be ready for some ablations and distribute your work amongst your study groups. As mentioned, the embedding layer is optional but not recommended. It is used to increase the dimensionality of the input.
Sorry, it is recommended but optional, I think.
Yeah.
But yeah.
So our task is to increase the number of input dimensions from 15 to a set number of dimensions. Say you can call it embed dim or any particular value of your liking, but definitely increase your dimensions, because that will really help your models to learn better. So given that we have time steps and features, you may have guessed it that we would be using Con1D layers for this homework. Here is a problem where we have the number of features restricted to be 15, and we have, say, 100 time steps. We want to increase the number of features from 15 to a set value. This would require you to transpose or permute this entire input in such a fashion such that your features get inflated and you can calculate hidden features like such. So your input features are now inflated to have more hidden features, as you can see in this diagram. What we have used here is a filter of size 5. So our in channels, which were basically 3 in previously, are now mapped with 5 filters. and we have the padding in place such that we do not downsample, and we are using a stride of 1, so it does not downsample our original input. That said, yeah, this is how we converted a 3D three-dimensional input to a 5-dimensional input. So our our input is of shape, batch size, time steps, and 15 before padding, after padding, and we can change it to a batch size, time step, and a size of 64 using these convolutional layers or these embedding layers. There is one parameter that I would like all of you to make note of, which is batch first. This will be used in approximately all the LSTM functions that we have. So make sure if you're using such an input shape for your models, make sure you set that as true. So the way to calculate hidden features would be to first transpose or permute, as I mentioned, to make the number of channels as the feature where you want inflation, where you want the inflation to happen. You apply a convolutional network, you increase the number of filters, you can set the number of filters, and you can increase the number of features from 15 to 64 as in this example, and then transpose it back so that you can pass it to an LSTM layer or a GRU layer. As you know, a stride of 1 will maintain the same input size, but a stride of 2 can help you downsample. So keep a track of the lengths, because LSTMs would require what length of sequences are you processing in an input. You use the lengths in the pad packed and the pad packed sequence before passing it to an LSTM. I'll be going it through in the starter notebook, so you'll have a much better idea there. A stride of greater than 1 reduces computation, as you know, because we are downsampling now. So LSTM training can be done faster. Although in this homework, we recommend you to not downsample by more than 4 times. It will lead to a huge loss of information. So my recommendation would be to not downsample by more than 4 times. That is one thing to keep in mind. You can use the convolutional formula to calculate the output shape after each particular, after your input passes through various convolutional layers. You can get some inspiration from what you have tried in homework 2, P2. You can take a ResNet block, a basic ResNet block. You can use bottleneck blocks. You can use a convex block. You may even create some customizable blocks of your own and just use them in your model. The sequence model, you can use either RNNs, GRUs, and LSTMs, which is available from Torch. Yeah, and this is how the sequence model would, the sequence model takes in some parameters. So it takes in the input size, which is the input features, in this case 15, or the embedding size. If you use a convolutional network and increase the number of channels, so our input size would basically increase. Then there's a hidden dimension, the number of layers, a dropout for the LSTM itself, and a bidirectional flag. The bidirectional flag, if it is set as true, you basically convert the LSTM layer to a bidirectional LSTM. You pass this output from the LSTM layer, from the sequence model, to the classification layer. There can be various variations in the in between. You can add, you can go for deeper classification networks, wider. You can also explore different types of activations and a dropout as well. For hyperparameters and regularization, you can use cepstral normalization. There are 2 other different types of transformation techniques which you can use. I will be talking about it as we go through the notebook. They are time masking and frequency masking. I'll introduce them shortly if we have time. You can use different weight initialization techniques for your convolutional networks and for your linear layers. A weight decay with your optimizer is recommended. This will help you get a better validation level time distance. A scheduler is very important. We have performed ablations using reduced LR on plateau and cosine annealing. Most of our ablations are with reduced LR on plateau. Cosine, so you may want to use that, but it's not a hard and fast rule. Cosine annealing, you may want to try cosine annealing, but be sure to train it for much longer. That would be my only piece of suggestion if you're using cosine annealing. Dropout is key in this homework. Even though your architecture matters a lot, we would recommend you to regularize your network thoroughly, because getting to the high cutoff, the cutoffs would be released soon, and regularization would be key for you to get to the high cutoff. A log dropout is much recommended if you want your model to generalize well. So instead of using the dropout from LSTMs directly, which is there as a parameter in the LSTM cell of Torch's implementation, we would recommend you to use log dropout within LSTMs. You can try various techniques to regularize your models. There are techniques like adding Gaussian noise, Gumbel noise. So adding noise would basically perturb your inputs and would let the model understand a slight perturbation in the inputs does not actually mean a huge deviation in the output. So addition of noise can be a good technique to regularize your networks. These are the two types of transformations that I was talking about: time masking and frequency masking. There is a link to the documentation here as well. I will explain how time masking works. So in time masking, a random sample or a random fraction of the entire input is basically dropped off and marked as 0. As in this case, you can see this example. We set a time mask value of suppose 50, and it basically drops off the first 50. Oh, I'm sorry. This is the diagram here. So here is the original input, and if suppose you have a time frequency mask of some said value, it will basically randomly choose a range and would drop the entire and would basically mask the input in that time frame. Frequency masking does the same thing, except for in the time, it does not work on the time axis, it works on the frequency axis, where it basically masks off any number of said channels in the frequency domain or in the frequency axis. I think the diagram is pretty self-explanatory. So yeah, moving on. Beam width. Beam search can be implemented using the CTC decoder, CTC beam decoder library that we will be using in homework 3P2. We recommend you to use a small beam while training, because if you use a very high beam, because if you use a large number of beams while training, this will increase your training speed exponentially. We recommend you to use a beam size of not greater than 5 for training your models. But in test time, you can use a beam size of a much larger beam size. So maybe you can go up to 20, 50, or any particular value that can be based on your experimentation. So make sure to use a higher beam size when you're testing your models. There are some final tips that make sure to split your work amongst your study groups. This homework will take some time. We recommend you to start early. Experimentation is key in this homework. Deciding upon an architecture is key, and also regularizing your models is very important for this homework. I will start presenting the homework to homework 3P2 starter notebook. But before that, do you have any questions?
Yes, so Pranav, for the early submission deadline, right? So
Yeah.
what models do we have to expect? Because I'm a little time constrained and I wanted to just do the early submission right now.
A very basic model with just an LSTM layer should work for you. We have
I think
attached
the
some
difference is that if you take the code from the previous ones, the data load has to be changed with padding, right? That's the difference.
Yes. You have to account for padding, and you also have to create a collate function. So I'll go through the notebook. Things will be much more clear and simpler once we go through the notebook.
Cool.
But any other questions from the slides?
Can we talk really quickly about the so that the packing?
Yeah.
I think it's like slide 20. Actually, yeah, 10. So
Yes.
we're going to be mixing frames from different files. Is that a correct understanding?
Uh, yes. So basically, so we have different elements here, and we sort them in descending order.
Okay.
Because LSTMs expect a uniform input so that they can handle these inputs, and they have to be of the same length. So that's why LSTMs use packing so as to process a batch of items together. So that is how packing works. So the element 2 in this example, being the largest, is sorted first, followed by element 0, 1, and 3. And then we take the first elements across all these first value across all these elements and put them here. And then we take the second element across all these samples and then put them next. So that would be our time step 0, time step 1. Then we use time step 2. Since we do not have a yellow value, since we do not have a value from the yellow element, we basically do not have something here for time step 2, which belongs to the yellow element.
I see. Well, the LSTM want to know, for example, let's just say we're processing element 2. Would the LSTM want to know something about the second row of row 1 of element 2 when it's trying to determine what row 0 is?
So when you unpack this entire input, if while passing it to the classification layer, you have like broken down the information again into batch, time step, and the frequency. So that would actually take care. It would actually take care of everything. You do not have to manually permute back to the exact shape as it was.
Okay. I think things will become a lot more clear when I start doing the notebook.
Okay,
Thank you.
no problem. I'll head to the notebook if we are done. I'm going to skip over the install section. It's just some just some basic commands of how to install some libraries and set up OneDB. So I'm just going to skip installs. Kaggle setup is pretty easy. You just have to paste in your Kaggle key and username, nothing else. This is just for mounting Google Drive. Onto the data set and data loader, as Abu had mentioned, we are replacing the pad token. So there is no need for a pad token explicitly. We just need a blank token as this. You may use this notebook here on if you have not started with your homework 3 part 2. But you can, other than that, you just need to copy paste this particular cell and just paste it in your already existing notebooks. Okay. So we are now creating the dataset class for this particular homework. So we expect you to have some basic understanding of what the data is. So as it is the same as from homework 1, there is an MFCC directory and a transcript directory. You be sure to use both train clean 100 and train clean 360 as they are mutually exclusive when you are making your final submission. So load all the files from these 2 particular folders while making your final submission. And for experimentation purposes, I would recommend you to use train clean 100. Although you can use 360 or even both, but working on a smaller sample will make life easier for you. There are some questions which I've left as to-dos. What should the length of the data set be? This should be fairly simple given the fact that you have completed homework 1 and homework 2 now. What you need to do is that you need to create an alphabet mapping dictionary here, because tensors do not take in string values. You need to manually map, or you can just write a particular code to create a dictionary which maps each particular alphabet or the labels which we have declared here to the alphabets or the labels. You can infer it from both. So you need to map them directly to and have a one-to-one correspondence between an alphabet and an index. These indexes would be the Ys or the labels for your network or for your model. So once you have declared the MFCC file directory and the transcript file directory, and also got all the, using a glob, you can, or like os.list directory, you can retrieve all the files in the directory. You will loop through each one of those files. You can choose to apply septal normalization here after reading the MFCCs. Append the MFCCs and transcripts to two different lists, which you can call X and Y, or maybe MFCC and transcripts. Replace the phonemes using the mapping, using the alphabet mapping dictionary, which we created here, because again, alphabets are strings, a model, tensors cannot expect strings. You can replace them and make sure to remove the SOS and EOS token as well. You may recall this from doing the same thing in homework 1 part 2. There are some to-dos here. We definitely would recommend you to complete this out or fill them out. Now you may choose to apply some transformations here in the collate function or in the get item function. There are some pros and cons of applying transformations in the get item and or in the collate. If you apply those transformations in the get item function, you are basically allowing for more variability, where each item is randomly masked, or each based on the time axis or based on the frequency axis. So this can help generalize your models better, but this comes with a con that training takes more time, because each time when you're calling, each time when you load in a batch and send it through your model, get item function, the get item function is called over and over again to make that batch. So applying a transformation each time in the get item function can be a little time consuming. So this is a trade-off. You can choose to apply transformations here or in the collate function. Both would work just fine. Now onto the collate function. In this function, you expect a batch as input. The batch has a shape like such. It is a tuple of MFCCs and transcripts, both like this. So you have to first create a batch of MFCCs, just the MFCCs. You may write a list comprehension for it if that makes the life simpler. And you would also want to write a list comprehension or just extract the transcripts from the batch in this particular variable. Now you can pad all the MFCCs. Now, given the MFCCs are of varying lengths, and your model cannot process inputs of such varying lengths, so you would have to pad all the input or the MFCCs that you have using the pad packed sequence by PyTorch. I would definitely recommend you to go through the documentation for pad packed sequence and check what it expects as its hyperparameters, as its parameters. So definitely check that out. Then you want to create a lengths array which would store the original lengths for each MFCC. This is very important because you would need it to calculate the Levenstein distance. You would have to slice each particular MFCC recording at some point. So this would help understand at what point does your input to the model end. You also need to pad your transcripts, because there has to be a one-to-one correspondence with from a frame level MFCC to the transcripts. Then you would also want to store the lengths of each transcript. Again, this would be helpful when calculating Levenstein distance. Finally, you return a tuple which comprises of the batch MFCCs, the padded version of the batch MFCCs, a padded version of the batch transcripts, and the lengths of each of the lengths of each particular element within the batch for MFCCs and transcripts both. The test data loader is a to-do for you. Referring from the train data loader, you can fill out the test data loader. It should not be a huge task. There is a batch size. We have initialized a batch size of 64. You can increase if you want, if your device can handle it. There are two types of transformations which we recommend, time masking and frequency masking. You can choose to define them here and pass them as a parameter into your data loaders while creating these objects here. So you can just specify the type of transformations you want to do to any one of the data sets. You would not do these transformations in the test for sure. And yes, you can also use the train data set as your validation data set. Just add a flag signifying which is which. Moving on, yeah, you have to create some data loader, validation loader, and test loader objects here. Here is a sample input. You may want to verify this once you are done creating your data loaders and dataset class. Here is a sanity check, which can be helpful for you as well. Moving on, so for the basic model, we recommend you to use a simple LSTM layer. You may want to look at the documentation, and as I did mention, some of the hyperparameters or the parameters that you can use, which is mentioned in the slides as well. You expect the input size, which will be 15 in this case, if you're not using any convolutions or creating hidden embeddings for your input. You move to a hidden size of 256, and you have just one layer for this simple LSTM network. You can try increasing the number of layers. You can add dropout. You can make it bidirectional. Refer to the slides. All the hyperparameters are listed there, or also to the Dodge documentation. You have a classification network here. So you can have basically a classification network sitting on top of LSTM cells that you have, the LSTM network that you have here. There is a log softmax that you would want to apply, simply being that you would want to get probabilities out of your classification after this affine transformation that you have performed here. So the log softmax would turn this affine transformation into just probabilities and give you the probabilities for each particular phoneme. So moving forward, how would the forward function work? First, you need to pack all the inputs, which are the x's, such that for batch processing, so that the LSTMs can process each batch item and do it much faster. Then after you perform this, after you get an output from the LSTM, you have to unpack this output. Make sure to go through the documentation for packing and unpacking these in the input and output respectively. Unpacking would give you two parameters as output. It would be the output in itself and also the length. So the length would be helpful if you want to do any kind of downsampling afterwards, if you want to add any kind of convolutional layer here. So that can be helpful. You can pass the outputs through the classification network here and apply a log softmax. Yeah, moving on to the criterion or the loss function, which we will be using. You can create an object of the CTC loss and specify the blank token ID. We have assigned the blank token ID with an index of 0, I guess. Yeah, this is the blank token, and we have manually assigned it to be at index 0. So make sure to specify the correct blank token ID. Yeah. Create an optimizer. This should be fairly simple. Create an object for the CTC beam decoder. All other parameters would stay the same except for the 3, the labels, beam width, and blank ID. So make sure you pass in the correct values for these parameters. Create the CTC beam decoder object. Initialize a scheduler and use mixed precision if you want it. Now, while calculating Levenstein distance, the CTC decoder has a decode function. The decode function gives you 4 outputs: the beam results, beam scores, time steps, and output lengths. The beam results are basically results from each given beam search that we perform. The beam scores are basically the CTC score for each beam. You can print out the confidence for each beam being correct using this particular formula. The number of time steps at the nth output character at when you have peak probability from your beam search. So the time steps parameter the output from the CTC decoder would then basically point you to that particular time step where you have peak probability. Output lengths is a parameter where is another output from the decode function where we have the results for each beam search. So for each beam and for each item within the batch. So make sure I can actually point you how to understand the shape of it here. Okay. So these are the inputs to the CTC beam decoder. I definitely would recommend you to look at the inputs and what its values should be. The decode function here takes out, we expect 4 results from the decode function: the beam results, beam scores, time steps, and output lengths. The beam results is of this shape. The beam scores is of this shape. The time steps is of this shape, and the output length is of this shape. As you can see, the output length is would basically give you the length of the jth beam result, which is the second index, and for each item in your batch, which is the first index I. So this should be fairly simple to it should be fairly simple for you to decode the outputs from your beam search now. One error which you may face is when declaring the batch size. The batch size will not be config of batch size. So try to think of an edge case where the batch size would not be the same as config of batch size. You may get some memory errors, or Colab may throw you out of your session. There are some weird errors which you may encounter here. So this is a basic follow for you to decode each particular sample in your batch. You can then reverse encode the results from the beam search that you got, and using the dictionary that we created, which was an alphabet to an index mapping dictionary, reverse encode that dictionary, strip the outputs down to a particular length, because you would need to strip them out to be of even lengths while calculating the Levenshtein distance. Otherwise, you would be taking into the padding into consideration as well. Yeah, and this is a sanity check for you to check whether you have completely whether your model is working fine. So if you follow these steps, you should be fine. I think we have made these steps pretty clear, and you should not face any problems following these steps. In the evaluate function, yeah, so the evaluate function should be fairly simple, given the fact that you have actually used you have created functions to calculate the Levenshtein distance, and you can infer from your previous homeworks on what exactly does the evaluation function takes in. There are some flags like model.eval and model.train, which you have to be sure of. So make sure to use them and implement them correctly. Apart from that, this is a train step function which we expect you to fill out. Once you are done with the train step and evaluation step, there is just the train loop where you call in these two functions one at a time. One piece of advice I would give you is that calculating the validation Levenshtein distance for each epoch will take some time. So you may want to skip it and calculate it alternatively. You can use the validation loss if you're using a reduce LR on plateau for your scheduler to step on. And I would definitely not recommend you to calculate the Levenshtein distance for your training. It will take a lot of time and it would just slow down things for you. Yes, and after that, you just have to create another. So before I conclude, just one last thing, you have to create another CTC beam decoder object here with a high number of beams, so that you are much more confident of your predictions at test time. Create a function called predict, which would help predict and generate these predictions. You can then create the submission file and upload to Kaggle. Yeah, that is most of it. Do you have any questions?
So Pranav, in the data loader part, can you scroll up to the beginning?
Yeah.
Yeah, so here this looks similar to what we did for P2 or P1. This is something which is similar. So I was wondering about the padding stuff, which was happening. So since you said that you have to do it, there is variable length, right? So
Yeah.
how do I? So basically here, right? You're talking about batch MFCC pad and batch transcript pad. That's where all of these things go.
Yes. So you use the PyTorch function of pad pack sequence to actually implement padding here. Uh, so pad pack sequence expects the input and the batch first flag and a padding value here. The padding value by default is 0, which also points to the blank token that we have defined for you.
Okay.
Batch first is basically a flag which would help just let the function know that the input shape is of batch size, time step, and frequency, or it could be of time step, batch size, and frequency.
I
And
see. Okay.
the sequence is basically the input.
Okay. Got it.
Any other doubts?
Can you please go over the alphabet map or once again?
Yes.
Yeah. So you said that we had to alphabet to index, right? So is that what you said? Like, what is the mapping that you, in the train function that we have to do?
So you need to create a mapping from the labels to an index, because you cannot have the Y's as phonemes or as alphabets. So you basically create a dictionary where each alphabet is mapped to a particular index, and that's how you create your transcript, which will be fed as which will serve as your labels or your Y's for the model.
Okay, thank you.
You can refer to the homework 1 P2. You have done a similar thing in homework 1 P2. So check that out.
Yeah, okay. I'll do that.
Any other questions?
Like in the CTC decode function, we are getting 4 outputs.
Yeah.
Yeah, and like if you go down, they are saying that the first item in your batch will be this, but I'm not able to understand, like outline basically is like the shape of sequence length cross beam width, right? So how do we understand out length? As in, like, what is that exactly?
So you
It
have a
says
number
it's
of
batch size
beams.
cross n beams, but I'm getting a out sequence length of. Okay, I'll just check again maybe.
So outlens is basically stores the results for each beam search. And so if you imagine it this way, the outlens has the beam search results for each item in your batch, which suppose if you're talking about the ith item, you have the beam results for the ith item and for the jth beam.
Right.
Okay, so this should give you back the output of your after your beam search.
Okay. So should we use this out length in the Levitian distance, or should we use the one that we have from the target information, or do we need both of them?
I would probably let you that figure it out.
Okay.
If there aren't any questions, I think maybe we can wrap up.